Welcome to Tripping the Light VR. Thank you for coming this afternoon. We have three great talks lined up that cover a wide spectrum of things covering and things around the space of virtual reality. So a couple of things to note. There is a discrepancy between the order of the presentations in the printed booklets and what's been in the app and on the web, so we will be following what's been on the web. So the first talk will be the making of Welcome to Lightfields VR, and this will be presented by Ryan Overbeck and Paul DeBevic. Ryan has spent the last 6+ years at Google Incorporated, where he currently researches compression and real-time rendering for light fields, and previously helped to develop the core rendering and navigation engines in Google Earth for maps. Before that, Ryan received his PhD after studying under Professor Ravi Ramamurthy at Columbia University, where he focused on leveraging ray coherence for high-quality rendering. Paul DeBevic is a senior scientist at Google VR and an adjunct research professor at the USC Institute for Creative Technologies. Since his 1996 PhD at the UC Berkeley, DeBevic's publications and animations have focused on photogrammetry, image-based rendering, high dynamic range imaging, image-based lighting, reflectometry, facial animation, 3D displays, and VR. Paul received SIGGRAPH's first significant new researcher award in 2001 and a Scientific and Engineering Academy Award in 2010 for the light stage facial capture systems. He recently served as Vice President for ACM SIGGRAPH and co-chairs the Academy of Motion Picture Arts and Sciences SciTech Council.
Great. Thank you, Chris. Thank you, everybody, for coming. I'm Ryan Overbeck from Google. I put together this presentation with Paul DeBevic, Daniel Erickson, and Daniel Evangelakos. And today I'm going to be talking about Welcome to Lightfields. It's a free app available for download on the Steam store. And this is really the first time that people can download panoramic light fields like these onto their own computer and view them in VR. And these clips might look like we took a video camera and walked through these scenes, but these are real renderings from our system. This is really what it looks like when you look at Welcome to Lightfields in VR. And Google and others have been looking into this sort of immersive photography for a long time now. The ability to take people to exotic places without having to pay for a plane ticket. And they've tried a bunch of different technologies to try to accomplish this. One technology is photogrammetry, where you take a bunch of pictures of a scene and use computer vision to generate a 3D textured model. And this is used in Google Earth VR. Valve has a great demo of this in the lab on Steam. And there are companies that focus just on photogrammetry, like capturing reality. Now, photogrammetry is really great because you can wander anywhere in the scene, you can view the model from any direction, but you generally lose view-dependent effects like reflections that just get plastered onto the geometry. And you can see that here in the Atomium in Belgium. This model is supposed to be reflective like a mirror. And complex geometry like trees are really hard to model. And so even the best photogrammetry models can look a little bit video gamey and aren't quite like being in that real-world place. Another approach is stereo panoramas, which you see here in the flight deck of the Space Shuttle Discovery. Google launched a couple products based on stereo panorama video with Google Jump and VR 180. Facebook launched Surround 360. And there are studios like Felix and Paul and Jaunt VR that also make stereo panorama video. Now, stereo panoramas tend to be more photorealistic than photogrammetry, but you're limited to a single viewpoint. You can only rotate your view. And also, as you look up and down, the imagery warps. And also, if you tilt your head, you lose the stereoscopic effect. And because of these things, people can sometimes feel a little bit uncomfortable or even a little sick when viewing stereo panoramas in VR. Now, light fields offer a whole nother level of realism. You get the full 6 degrees of freedom of movement, that's both rotation and translation, within a limited space. And you get this full freedom of movement while maintaining photorealism. And so static scenes like this come alive with dynamic effects like reflections that you can see in the monitors here, or transparency through the windows. Also, your movement in VR matches your movement in the real world, and so people tend to feel comfortable when viewing light fields in VR. Light fields really are like photographs that you can step inside of and move around. So we've been researching light fields for a while now, and we wanted to share our results with everybody. So we built a couple light field cameras. We captured a bunch of light fields. We wrote up this app, Welcome to Light Fields, with the help of Unity, and we launched it all to the Steam store. Now, I'm assuming some people here haven't seen the demo yet, so I wanted to show a couple clips of it here. And if you haven't seen it yet, please come visit us over at the Immersive Pavilion, where we're showing live demos. So Welcome to Light Fields includes a little guided tour that explains what light fields are and shows you around a few scenes. And then there's a gallery of 34 light fields that we've collected. And we worked really hard to collect a wide variety of scenes that show everything that light fields have to offer. So thanks to a really great collaboration with the Smithsonian, we were able to collect a bunch of light fields inside of the Space Shuttle Discovery at the National Air and Space Museum in Washington, D.C. So you can see what it feels like to be inside of the Space Shuttle's cargo bay here. And our light fields are really great for getting a true sense of scale, so you can stand outside the Space Shuttle and really see just how big it is, or how confined it is in the flight deck. Now, I already pointed out the reflections in the monitor, but our light fields are also really good at getting really intricate geometry, so you get motion parallax even on the little switches and dials, especially on the ceiling here. We also worked closely with a 3D photographer, Greg Downing, who helped us collect a bunch of light fields all around California, and we collected several light fields in the Gamble House here. Now, the Gamble House has lots of this finished wood with these beautiful glossy reflections that show up really nicely in our light fields, and you can see the reflections in the vases here, too. And this one is one of my personal favorites. The St. Stephen's Church in Granada Hills has this beautiful stained glass window. And as you move your head side to side in the light field, you can see the light just peeking through the little panes of stained glass. And I don't know of any other technology that can capture this kind of thing in real-world scenes the way light fields can. And we can capture people, too. And so we did a photo shoot with artists Sherry and Gonzalo here, who started tiling their bathroom one day and never stopped. They covered their entire home in Venice, California, with these little colorful and reflective pieces of tile. So light fields have been explored for a long time now. In academia, they were introduced to computer graphics way back in 1996 with two papers, Light Field Rendering by Lavoie and Hanrahan, and The Lumigraph by Stephen Gortler and others. More recently, Otoy showed a demo of light fields using early Oculus Rift development kits. And last year, Lytro showed off light field video in VR with a piece called Hallelujah, but it did require specialized hardware in order to display them. And none of these works really meets our goal of using fast and affordable camera rig to produce high-quality panoramic light field stills that you can view with consumer VR devices. And as you can see here, you can view Welcome to Light Fields on a commodity VR-ready laptop and view it in consumer 6DoF HMDs like HTC Vive, Oculus Rift, or Windows Mixed Reality headsets. So with that background out of the way, the rest of this talk, we're going to talk about how we acquire, process, and render our light fields. And to help talk about how we acquire them, I'm going to hand it over to Paul DeBevick here.
Great. Cool. Thank you very much, Ryan. So the basic thing that we're trying to capture is all of the rays of light that are coming into a sphere of space about this big, about as far as you can move your head from a standing position or from a seated position. And kind of an early concept of this was to put cameras basically on a spherical surface and just capture all those rays of light at the same time. This would work for spherical light field video, and then you could see that on the headset. We didn't want to go ahead and build this big complicated thing first off. I certainly didn't want to pull all the micro SD cards out of this thing to read them out. And so we decided that if we limit ourselves to still scenes, we can use a subset of the cameras and move them around in order to capture the light field stills. And so this is the device that we built. You can see it in the immersive pavilion. And it's based on a GoPro Odyssey, which was built with our Jump program from Daydream. It originally started as 16 GoPros tightly packed in a little circle to shoot omnidirectional stereo from the two fixed left and right eye viewpoints. But we stretched it out into a wider arc and then put it on a motorized rotation gantry that allows us to get all of those spherical points of view. And it's designed specifically so that we can take it places, take it with in our luggage in an airplane, and also set it up relatively quickly. So you don't actually need 4 people to do this, but you can see that in about 10 minutes you can get it out of the suitcase, set it up, and be shooting a glorious light field at that point. If you take a long exposure of what that rig looks like when it's going around, the power indicators of the GoPros, if you don't turn those off, actually kind of trace out the shape of what's being captured there, so you can see the sphere of viewpoints occurring. And then the visualization on the right side of the slide is showing basically how light field rendering works. We're capturing images on the periphery of the sphere, which record these rays of light coming in. But when the person's in VR, we need to render views that are inside the sphere, and we never really put cameras inside the sphere. So we're going to use the rays of light captured by those cameras that went on the outside of the sphere to compose new images based on pieces of those different images to show what you would actually see in your headset in VR. So you can see, for example, on the orange image there, those rays of light can produce one viewpoint, and then you'll reuse different pixels from some of the same images to produce another viewpoint from another perspective. Because all the rays of light you need for an image inside the sphere at some point had to cross the periphery, and we put a camera close to it. If one of those rays of light that you need actually went between 2 of those cameras, we use view interpolation techniques based on depth maps that Ryan will talk about later in order to produce that. So this is the rig actually in operation inside Space Shuttle Discovery. We did take into consideration the distance between the pilot and commander seats when we built the rig, and that kind of dictated the headspace that we had for some of our earlier captures. That sped up a little bit. I think we were running it in around about a minute. And the nice thing about this rig is that it's just fast enough that you can take pictures of people if they're willing to stay still. So we actually after we had recorded some of their house, we asked Sherry and Gonzalo in Venice if they would be willing to pose for a couple of portraits out in their creation that they had of their front yard. And fortunately, they were happy to do that. We had the question, kind of as a photographer, where do we tell them to look? Like, where's the lens? There's lots of lenses, and they're moving. So the first thing that we asked them to do is just stare at the post in the middle of the thing. Which is a little bit hard because you've got stuff moving across your visual field. And the result is that when you're looking at the light field, you have these people in there that are just kind of staring into space, and you can kind of move into their field of view, into their gaze direction, and move out, which is a little bit odd. So we had an idea of another way to shoot the light field, where we actually asked them to watch that little piece of green tape that we had on that side and the other side and on the front. That indicated the center camera, and just follow that with their eyes, otherwise keeping their neck and their head still. And the result of that, you can see, this is literally the video feed off of the central camera of our arc. You can see they're kind of following it with their eyes. Right before, Gonzalo blinks right at the very end there, but he was pretty good. And the result then is that in the light field, every view shows them looking back at you. So as you move your head back and forth, they actually are paying attention to you. They are themselves kind of frozen in space with their architecture. You get some nice reflections on the window behind them. But this seemed like the better way to do portraiture. If we have more time to record a scene, then we thought it would be nice to use image quality that's a bit higher resolution and higher dynamic range than what we can do with just GoPro cameras. And so we also built a version of the rig that uses mirrorless cameras such as the Sony Alpha 6500. And again, we wanted to make this really easy to pack up, so we wanted to use the same drivetrain that just rotates the thing. But now since we have fewer cameras, we actually have to have those tilt up and down somehow. And the way that we did that without having an additional motor is we actually used an idea that came back from the very first light stage from 1991, which got a light source to move around to all the positions on the sphere in a spiral using a string that unwinds. And so we actually made on the top there a little spool that has a string that's wrapped around it, and as that single motor turns this around, the string slowly unwinds, and it produces a spiral like you can see in the light stage. And the equivalent spiral that you can see here, there's the string unwinding. And if we put like an LED on each one of the cameras to trace it out, you can see that it produces a relatively well-calibrated data set of different positions. You also notice that there's kind of a bright dot as it goes along. That's because we actually have a mode where you can tell it to dwell on a position. If there's less light and you want it to stop and you can take a longer exposure. It also gives us the ability to shoot high dynamic range. So here we are in the cargo bay of the space shuttle, and you can see it stops every so often, and it's actually shooting high dynamic range images with plus or minus 2 stops at every position. And that gives us the ability to have a higher dynamic range light field that we have more latitude in the tone mapping process in order to try to make it look its best in the virtual reality headset. So those are the two rigs that we were able to build and that produce the things you'll see in Welcome to Light Fields over in the Immersive Pavilion. And I'd like to turn it back to Ryan Overbeck to talk about how we process and eventually render these light field data sets. Thank you.
Awesome. Thank you, Paul. Right, yes, thank you. So after we collect the images with one of those camera rigs, and before we can render them, we have some processing to do. And so we wrote up a fully automated cloud-based pipeline to prepare these images for rendering. And so the first thing we have to do is calibrate the images, where we get the position, orientation, and lens information for every image, and this is a visualization of some of our results from that. And you can see at the top and the bottom there are holes, and that's because at the bottom that's where the tripod is, so you can't get cameras down there. And at the top, we don't always wind the camera all the way up to the top to save a little time in the shoot, so we sometimes end up with a hole there too. So to cover those holes, we use offline view synthesis, where we interpolate the images close to the holes and add images to the light field in order to cover those holes. Now after that, you see the distribution of images is a little uneven. It gets denser kind of towards those holes and then a little sparser elsewhere. So we remove some of the images in these denser regions, and we end up with a really nice even distribution of images all over the sphere. And then we extract depth maps because we use the depth maps for our rendering algorithm, which I'll explain later. So we take a neighborhood of images around each light field image and use multi-view stereo to generate these depth maps. And then to make them efficient for rendering, we convert those into a triangle mesh. We first make a dense triangle mesh out of it, and then just use a mesh simplification to get it compact for storage and rendering. And then our light fields tend to have 1,000 to 2,000 images, which tends to be about 4 to 8 gigabytes uncompressed, so we need compression. And so we modified the VP9 video codec to give us our compression, and our modifications make it possible to load the light field in compressed form so that it doesn't take up too much memory and just decode the parts that we need when we need them. And we were actually able to get these changes into the upcoming AV1 codec, and so soon anybody can compress light fields using this method. And after compression, you end up with a file that's about 50 to 200 megabytes, which is pretty good for download. And this is with the highest quality settings turned on. So you end up with this nice compact light field file, and it's ready for rendering. And there are really two big challenges for the rendering. First and foremost is quality, because any visual artifacts really hurt immersion. And then, of course, second is speed. We need to render stereo views at 90 frames per second, which is really fast. That's 2 views. You only get about 11 milliseconds to render both of those views. Fortunately, we came up with a pretty good algorithm that handles both of these really well. And to describe that algorithm, I'm going to go back to the flight deck here. The frames of this video were all rendered with our system. And so our renderer is blending together hundreds of images in real time to generate each frame of this video. And this is what one of those images looks like. So we projection map the image onto one of the depth maps that we generated in the processing pipeline. And you'll see if you just look at this one image, it looks okay towards the middle, but then out towards the edge, it gets really stretched and doesn't look so good. And the reflections don't move. They're just plastered to the geometry. But if you look through just a little window like this little dish-shaped window, things look pretty good because the rays going through that window match closely to the rays that captured that picture. And then if you do that for every image in the light field, where you have all these little dish-shaped windows that look onto each texture map, depth map in the light field. So with this light field, there's about 1,000 of them, so that's 1,000 of these little windows. You get this, and then if you grow those disks so that they overlap and blend them together, you get this nice cohesive view of the scene. You get really high quality rendering without disturbing artifacts, and we can render these consistently at 90 hertz on VR-ready computers. So that's an overview of how we do the rendering. Please join us tomorrow. Daniel Erickson is going to give a talk over at the Unity booth, which goes into more detail about how we made a light field plugin in Unity and used that to make it easier to add audio and mix our light fields with photogrammetry and things like that. And then we've been busy working on the next step for light fields, and I'll give a sneak peek of that here. The biggest request we've had since we launched is, can I please get some more room to move around in? And so we stretched out the arm on our DSLR rig, and now you get a full meter to move around in, which makes a huge difference. It's way more comfortable to look at these newer light fields. And then we also get a lot of requests for movie quality synthetic scene rendering. So we rendered about 1,000 images in Maya. Each image takes hours to render, but then we feed those into our processing system, and we're able to view this scene in real time. And then, of course, light field video is really exciting. We've got some very early results here. We have this prototype rig that we built, and we've got some early results. We've still got a lot of work to make it fully immersive and to make it practical for delivery, but we've got a good start. So please download the app if you haven't already. It's really easy to find up on Google. And please come and visit us in the Immersive Pavilion to get a live demo. We have some of these more recent results that I just showed playing there. And then we have a paper that is now conditionally accepted that goes into way more detail on how we do everything, so keep an eye out for that. So of course, lots of people went into this work. Thank you everybody who's here and not for helping us out there. Thank you all for paying attention, and we're ready for questions, I think, if we have time.
Yes,
yeah, great.
There is time for questions, and if you do have any, please come up to the mics in either of the aisles.
Hi, my name is Dylan Lee. I'm from University of Maryland. My question is, what are some of the problems that you run into for video light fields? Because I feel like there's going to be tons of data coming in, and how you go around solving that problem.
Yeah, so compression is definitely one of the big issues that we're digging into. You're right, it's just a ton of data that we have to deal with. So we've got some early ideas on how to deal with this, but that's one of the things we're iterating on. The other is just getting quality. Like, you know, if you don't hit this quality bar on these things, it's really hard to feel immersed in them. And so we've got a lot of work to do to get the reconstruction algorithm to really hit that quality bar.
Okay, great, thank you.
Yeah, thank you.
Hey, what plans do you have, if any, to open up either the hardware or the rendering pipeline to creators, VR creators?
Right, so we don't have immediate plans for that yet. We're evaluating a lot of different directions we can take this. And that's one of them that we're looking into, but we haven't committed to anything just now. Like I said, we did put the compression algorithms into AV1, and the code's already in there, so you can see already how we compress and decompress light fields, but currently we don't have immediate plans to release the other stuff just yet.
Hi, is it possible to stitch together multiple light field captures?
You mean kind of composite them, like have multiple light fields and composite them together to make?
Meaning, like, could you capture a meter here and then move a meter over?
Oh, you could totally do that. I mean, that's pretty much what Lightro did when they created Hallelujah. There's definitely some work to do to composite them together, some work to get them to align well and all that stuff. Our current pipeline is really nice and automated, so we'd want to make sure we'd automate something like that, but it's definitely possible. Yeah.
I believe there's time for one more question.
Does the system require manual calibration every time before usage?
Yes, so we have to calibrate for every shot because the moving camera rig and the string mechanism makes it so that the camera positions aren't totally repeatable, so we do a full calibration for every shot.
What method are you using for calibration?
Right, we use code based on Visual SFM, which is an open source package, so you can look for that, and we use methods based on that.
Okay, thanks.
Yeah.
Calibration was going to be one of my main questions, so
okay.
I think you answered that. And then in terms of then post-alignment and so forth, you do it as part of your processing on the cloud then, or?
How do you mean post-alignment?
Well, in terms of, you've calibrated it,
yep.
But in terms of getting the images exactly lined up and, you know,
well,
does the calibration give you enough information?
That's exactly what the calibration does. It lines them all up, and then so that we know exactly the position in space where those images were taken from. And then the depth maps help align the images and that make it smooth as you transition between them when you're looking at them.
And then, so the Unity plugin, that'll take the AV1 format? Or
so the Unity plugin, yeah, we coded our light field viewer, and it just feeds directly to our viewer. So it's just an OpenGL stream. So it takes the light field in there, and then we use Unity to build the Chrome around the light field rendering.
Okay, thank you.
Yeah.
Okay, I think that's all the time we have for questions now. Sorry if there are any, maybe the presenters will be available afterwards, but let's thank our speakers one more time, Paul and Ryan. Okay, our next speaker is Johannes Sam. He will be presenting Fractal Multiverses in VR. Johannes had an early interest in 3D and began by teaching himself at home. Since then, he's studied at SAE Institute and Bournemouth University and worked at Scanline VFX and Rising Sun Pictures. Johannes has a Technical Achievement Award from the Academy of Motion Picture Arts and Sciences for his developments for deep compositing. Since joining Framestore, Johannes has continued to make advancements in the worlds of AR, VR, data point cloud workflows, and procedural generation. Johannes is constantly looking for opportunities to improve efficiency, better workflow, and creating solutions to creative problems.
Mac or PC? Thanks for the introduction. My name is Johannes Sam. I am at Framestore right now, and I'm representing a larger team of artists, designers, and engineers in the immersive entertainment division of Framestore. I'm here to talk to you about Fractal Multiverses in VR, and in detail about an experience called Coral VR, which is a fractal dive explorer in VR. So I'm going to go quickly through the overview of the talk. I'm going to give you a quick introduction to the project and how it was conceived. Then we will talk about design considerations we had to do at the beginning of the project, how we are transmitting a sense of scale, which is very important with fractals, obviously being self-symmetrical on different scales throughout the multiverse. Then I'm talking about locomotion. How have we approached the traveling through those fractals? And then I will spend the most of the time explaining to everybody how we actually get them to render at 90 frames a second. As Google has said before me, 11 milliseconds is our big number that everybody has to hit. So we're using a technique called conemarching. I will explain that. We also do a lot of stereo reprojection. And I quickly will explain also the shading and how we get the colors into the fractals. And then I will talk about future work and what we've learned throughout the process. So let me quickly switch to the Mac, because that's the only system where my video works. And give you while this is running, this gives you a quick introduction on how the experience works and how it looks. It's a side project and a pet project that was conceived over coffee between Aaron Hedgerson, our ECD, and myself, where we were just wondering how fractals would actually work in VR. So I went and made a little hackathon 1-week prototype that was running at probably 10 frames a second, and it was in grayscale. So it didn't really hit the mark that way, but we got an interest in it, and it really showed us how exploring those formulas is really helpful and really exciting as an art project. So from then onwards, we ventured out and made Coral VR. So let's start with a design consideration at the beginning. How do we transmit a sense of scale? As I said before, fractals exist at a multitude of scales and at a multitude of positions. So we had to figure out how we do this. So what we do is we scaling the interocular. As you might imagine, if you go to something really close, your eye stops being able to resolve that distance. So we scale the interocular as you're traveling through the fractals. That means you are starting at the size of a human and probably scaling down to the size of almost a bacteria and back out as you're going through the experience. We're smoothing this a lot because obviously squishing your eyes really close together and scaling them back up again is not a very comfortable thing to experience, but with a lot of smoothing, this actually happens without any users ever mentioning it to us. So it happens unknown to you. We also had to design the look and the colors of the experience to be different at each scale, so you don't get lost in the experience. So as you dive down and get smaller and smaller and reveal more and more detail, the colors slightly change, the petals slightly evolve, so you actually end up with a different look, so you know where you are currently in the fractals. And we also loop the fractals in the spatial domain and warp them in on itself, so we can literally travel for years in one direction and still see new content that's created for you at the time, hence the multiverses. So now, how do we solve the locomotion challenge? How do we move through the fractals? We experienced with lots of different models, moving along a controller. The problem with all those things is that you are in a very abstract universe, and it makes you getting lost and also introduces a lot of nausea. So what we do is we make a complete gaze-based navigation. So you look wherever you want to go, and then you accelerate in that direction. And then we're vignetting that. This is now a trick that has been around for a couple of years in VR experiences where, as you might know, motion sickness happens in your peripheral vision. So if you're in the car reading a book, it's not the book that makes you nauseous, it's all the stuff that happens in your periphery. So we limit the peripheral vision as you go really fast or as you move your head really fast to keep nausea to a minimum. So we're showing it at Immersive Pavilion, and we have probably shown it to a couple of hundred people, and one person got sick. We also link the velocity to the scale that you're in the fractal, because obviously if you're the size of an ant, you have a different speed in world space compared to a human to make you travel smoothly through those worlds. The way our rendering works, the collisions are coming pretty much for free. But they have been very disorienting for people. So if you run into a fractal and bounce back, people got lost. So in our current iteration, we have collisions turned off entirely, and you just zip through the fractals if you choose to do so, and we reset you to a more reasonable scale. So now that we can move through the fractals and have designed our experience as it is, the challenge becomes to how to go from my grayscale 10 frames a second demo to 11 milliseconds per frame for 2 eyes. So just to give you a quick overview what the problems are that we were facing is, as it's a distance function based approach, we have usually very expensive ray marching techniques that are used in offline rendering by very prominent fractal artists these days that have probably between 11 and 12 hours to render that, not milliseconds. So we're trying to obviously have to go down a lot on that. And as people travel through the fractals, more and more detail gets revealed, and actually renderings becomes more and more expensive. So we have to make sure we come up with a technique that is scalable. And we also have very high frequency detail and very chaotic texturing that makes it really hard for us to predict certain patterns and try to reuse patterns over time. And obviously we have to deal with a GPU, so floating point precision is a very big problem. As you get smaller and smaller and smaller, you have very, very small changes in floating point precision, and that obviously gets us into trouble. So let me give you a quick overview how fractals are usually rendered. There's a classic ray marching, where you have a distance function to the surface, and you start from the camera and you march at a fixed step size towards the surface, and if you get really close, you stop rendering. This is obviously very, very expensive, as you have to have a very small step size to get really, really close to the detail that you want to portray. So the next improvement on this algorithm is called sphere tracing, where you, again, start from the camera, and then you figure out where the closest point on the surface is, so you know if you now travel along the camera array, you can travel to the radius of the sphere without hitting anything. So now we jump to the radius of the sphere, then we rinse and repeat, and end up with way less steps at the surface, which is a very nice technique, and is the technique that is used in current fractal rendering solutions like Fragmentarium, Chaotica, Mandelbolver, as people might know. So this is our preferred approach, but it has overstepping issues and still doesn't get us where we want to be. So again, as we have the VR constraints of 90 frames a second, and also any sort of GPU stalls or waiting time would throw people out of the experience, we have to keep rendering 2 eyes at a time as well. We applying a technology or a technique called conemarching, which is a classic demo scene technique, which we first saw at Fractals by Fulcrum in the 2012 revision. What that means is we progressively render the same fractal at different resolutions. And each time we do a regular sphere tracing approach. So if you look at the diagram, I'm trying to render this box. So I'm starting at a very, very low resolution. In our case, it's literally a 2x2 grid. And we start sphere tracing in the center of each pixel. And we keep doing that till we hit a minimum distance, which is bigger than the actual pixel size in the world space frustum, as we see here. And then we stop, we split the image, we double the resolution, we reuse the depth from the previous pass, go back with a little bit of a bias, and do the same thing again. And if you keep doing that, you end up at the surface at the same position, but in way, way less time, because you're rendering the entire image at super low resolutions and then reusing depth from that distance. So that still means that we have now lots of parameters. So how many passes are we taking? How often do we split the image? How many iterations are we allowing per fractal? As fractals are very chaotic and very different from fractal to fractal, we expose those parameters to us and we tweak them by hand to get to the best results. So here you see the frame debugger output of one of those steps. You still see that we cone march, then we do our shading, then we do a little bit of post effects for one eye, and we do the same thing on the other eye. So as I click through this, you see how the different cone marching steps reveal more and more and more detail, and we get better and better and better at this. But even with this technique, we hit about 19 milliseconds. So we're not there yet, we're halfway there. So the idea is to, as you see here, clearly we're doubling up a lot from one eye to the other. So what we're trying to do is we're trying to remove the second cone marching step, which leads us to stereo reprojection. So this is the kind of new thing that we added to the rendering of fractals by porting it to the VR domain. So this is based on Oculus approaches and the paper called Fast Gather-based construction of stereoscopic images using reprojection. So what we're doing is we have two eyes to render. So we first generate a center eye, which encapsulates both left and right eye. We run our regular conemarching pass on those on this center eye, but reserve the very, 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 very last step at that distance. What that gives us is the ability to now reproject the depth from the center eye to the left and to the right eye. And because we still have to do one more conemarching step at the highest resolution, we can in-paint the areas that are missing from the reprojection. So because of parallax, certain areas are missed by the reprojection. So the last conemarching pass, as we're having the function that we can evaluate against, we in-paint those areas and now have a full depth map per eye. So here you see the result of the center eye. Here you see the areas which are missed by the reprojection step. And then after we do the final conemarching pass, we have now a full left eye without having to render twice. So now back to the diagram of my GPU debugger. Here you see that the conemarching step can be removed, and we end up with a big conemarching step at the beginning for the center eye, and a small, small, small reprojection step, and then we do shading and post effects on the left eye and the same on the right eye. And with this technique, we were able to get to 10, 11 milliseconds a frame. That leads me now to the actual shading step. So now we have a depth map for each eye, and the geometry has been created. But we need to address the shading problem and do that really quickly. So what we are doing is fixed foveated rendering. Because we are dealing with a headset that doesn't give me the actual eye direction, we just assume the center. So we on the periphery, we render with way less quality than we do in the center. And then we have a final compositing pass where we put those two together and apply a distance fog, and then it's absolutely impossible to figure out where the lines are. Generally speaking, everything that you know from regular rendering, shadows, occlusion, subsurface scattering, even just computing normals is horrendously expensive in the fractal domain. So what people usually do is a technique called an iteration glow, which is a technique where you use the amount of steps your sphere tracing took till you reach the surface and divide it by the max steps that you're allowing, and you get something that looks a little bit like ambient occlusion. As we have this conemarching approach of tracing it at different resolutions and constantly doubling the resolution of our image, we can't use that because we don't know how many iterations we actually had to take to get to the final result. So what we're basically doing for our shading is custom shader hacks. I will give you one example of the classic Mandelbrot fractal that we are using. So as I said before, even rendering or computing normals is super expensive, usually done by finite differences. Looks in code like this. So you step left, right, forward, backwards, up, down, to then figure out the gradients of your surface, and by that you can figure out the normal. But we would have to evaluate the fractal 6 times more than we already do it. So that was not really an option. So we are looking at fractal forums and all the usual shader toy and every fractal artist in the world that does this. And we found, for example, this trick by Nico Kules, IQ, who proposed a way to fake diffuse lighting somewhere on poet.net. And it shows you how hacky this all is. So he found out that just by stepping one time backwards in the direction of the light ray, you get something that looks a little bit like a diffuse. So that's the credo of our rendering, which is basically looking at all the signals that are coming out of the fractal computation, as obscure, as weird they might be, and combining them in an artistic way to figuring out the look that we want to go for. So here you see something that, a signal that we used which resembles of a diffuse. We can apply the same idea to ambient occlusion, subsurface scattering, and rim lighting. And then we get all sorts of different signals like this image which looks a little bit like subsurface. It is not subsurface scattering. It's just something that is a product of the formula who happens to look very similar to subsurface scattering. This is the same thing with rim lighting. So what we're doing, we're combining all those signals, and anybody who has been doing the shading work in our team is creatively using all the different ways that are out there to combine it. The only thing that's combined with all the fractals is we use standard cosine palettes to figure out colors. Again, a standard demo scene trick to be very, very fast. And at the end of the day, you get something that looks trippy and interesting like this. And on top of everything, we use a homogeneous scattering approach to do the Z-fog, which is a technique that actually was introduced to by Chris Howard probably almost 10 years ago when we did Captain America together, which is a paper that was released at SIGGRAPH, which is actually a paper that measures scattering by diffusion. So people put a light bulb in a solution and then measure how this specific light bulb diffuses over the distance of the box. And the paper is very, very interesting in some parts, but completely useless to us. But it has at the end a very interesting, 3-line single-way scattering solution that we're using. So it has been, coming with me since Captain America now to real time, which produces an effect like this. So you get an underwater look by the absorption of the colors of your fractal towards the camera, and then you add a light from a imaginary surface that you're underwater with, which gives you the kind of diving and underwater look. Which now leads me to conclusions and future work. We're only halfway there. We can do way more to speed this up. As you've seen, we've reprojected the conemarching and the depth estimation step, but we can do the same thing with shading. Oculus already does that in parts in their API, so that's obviously one of the next things we should do. We should also look into temporal reprojection. We might not need to render every frame. We can probably make up frames and depth maps as we go along and use the motion vectors as we do so. And we can also try to reproject other effects, like the glow and the bloom that we are applying in a post effect are low frequency effects that should also be easily reprojectable. We should also look into anti-aliasing techniques like TAA and FXAA, which should be easy for us to do because from our reprojection step, we know the outlines of all the shapes. So we know where we have to apply those techniques. We should also look into God rays, as they would look very pretty. Hopefully all those techniques will give us a couple of milliseconds so we can make it prettier by using God rays, because being underwater and having God rays would be obviously very, very nice. We can obviously optimize ray scheduling, go really, really deep down into the GPU. And also, what one of my biggest passions is, which we are trying to do right now in a little research project, is what we call sentinels. So it's like, if you think about the Matrix, it's about training networks that recognize shapes. So in a world where we have to create more and more and more content, and having less and less artists to do that, the idea is to train a network that recognizes the shape of a chair, a car, a spaceship, and then I go home to my wife and kid, and the sentinels start running into those functions, into the fractal functions at all different scales and parameters, and try to find shapes that are looking like what I've told them to find. And that they save the parameters, they save the space and the bounding box of those, and extract those and present them to me in the morning. So I can go back and actually use parts of those fractal functions in experiences that have nothing to do with fractals, using shapes that have been guided by fractals, using networks to find them. So we're very early in the stages in doing so, but we think we can get nice results in the future for that. So the core VR team is basically everybody who has ever worked in the LA office with our immersive technology division. So it's a bunch of people. Sadly, Mariano Machante, who authored the talk with me, due to visa restrictions, was not allowed to leave the country, as in the US. Thank you to everybody involved. Thank you for your attention. And if you want to try it yourself, you can go to coral-vr.com, give us your email address, download a copy of it, and start diving into fractals in VR yourself. I'm actually going to do a live demo of it right now while I'm taking questions. It's a very good tool if you have social anxiety. If you don't want to interact with people, you just put a headset on and you converse with people through that. So that I'm trying to set that up. If anybody has any questions or concerns, please let me know. Otherwise, I'm just going to spend 5 minutes tripping on the stage of SIGGRAPH.
All right. Thank you, Johannes. And if there are questions, again, please just come up to the microphones.
Hello. So could you elaborate on the benefit of truncating the final ray marching step before reprojection?
Yes, I could. Give me a second. So we're flying to fractal line. So yes, so the reason why we need to do that is we stop at a lower resolution, and then we need to in-paint the areas that we're missing. So if you think about me moving from left to right, there will be parallax issues behind that I'm not seeing, and that's why we reserve the last step to the actual for the actual ray marching to in-paint those areas, because the areas that have not been missed should already have a very, very close value to the surface. So we will not do any iterations there, and only the areas that have been missed will be in-painted by the algorithm.
I see. And my other question was, is there a reason you can't use some kind of screen space normal approximation, like at a second pass or something, for shading?
The issue for that is that we could, but we were running out of time actually to do this, because we have the depth maps at the very, very last stage, and by that time we have to shade the pixels. So if we would have to save that out and do some sort of screen space effect, we would need to have the entire result already ready. But you're right, trying to go into regular screen space normals or even screen space ambient occlusion based on a depth map is something that we should look into in the future.
So basically there's not even room for a post-processing
No,
step.
that's the problem. It's really hard to render fractals in 10 milliseconds, I tell you. We tried it for a year and a half. It is not easy. I'm just switching through different ones so to give you a bit of an idea of what's there. I also have the trippy music in my ear, like on half ears. It's really hard to concentrate. I'm sorry. So where am I now?
Right. Are there any more questions?
If not, I reserve the right to have 1 more minute of
Yes,
this.
Yeah, there is time. We can all watch you for that.
I do have one more question.
Yes.
Could you speak more to the sort of automatic sentinel generation of assets from fractal space? Why is that assumed to work? Like why would you go there?
It's assumed to work in my mind. So it is a research project. So I have no results yet. But having seen fractal shapes that look very, very interesting and different, and having also listened to talks at SIGGRAPH last year from old friends of mine at Animalogic that were actually for Ego's Planet, for Guardians of the Galaxy, literally doing that, but being the Sentinels themselves. So they obviously had a design that was very fractally. But I have seen shapes in there because the good thing is fractal artists probably spent the most time going through fractals, but it's not real time. So actually flying through and discovering new shapes and areas, in the standard fractals, we still find real singularities where suddenly the entire world repeats itself in a single sphere. And I have never seen those before on any forums. So just by the fact that I can dive through this in real time, we found really weird areas that resemble of other shapes that otherwise have not been discovered. So I have a feeling that if I send a render farm into the fractals for days, that they will find shapes that I want them to find is pretty high. But it's an assumption. It's future work. Stay tuned.
Thanks.
This is, by the way, a live stream from the inside of my brain right now.
All right. Let's thank Johannes one more time. Okay, our final talk today is VR story production on Disney animation cycles. And we have 2 speakers today, Jeff Gibson and Jose Gomez. Jeff Gibson is the director of the VR short film cycles. He graduated with a Bachelor of Environment Design from the University of Colorado at Boulder in 2008. After graduation, Jeff worked as a designer and project manager at Site Design Group Incorporated, designing over 80 concrete skate parks, both nationally and internationally. In 2011, Jeff switched career paths and began working in animation. His work experience includes Pixar and Leica House. Currently, Jeff works as a lighting artist at Disney Animation Studios. His film credits include Frozen, Big Hero 6, Zootopia, Inner Workings, Moana, Olaf's Frozen Adventure, and Ralph Breaks the Internet. Jose Gomez was a creative partner specializing in VR tool development and technology on Cycles. He studied computer engineering at the University of Salamanca and was an honors graduate from the University of Teesside in 2001 with a Master of Computer Science, focusing in computer graphics. Joining Disney Animation in 2013, he has worked as a senior software engineer on Frozen, Big Hero 6, Zootopia, and Moana. Prior to Disney, he was a VFX software developer at Digital Domain and Framestore working on feature films. His experience also includes work at Ilion Animation Studios and Bren Entertainment.
Awesome. Thank you so much for that introduction.
Thank you, Pete.
So what's